Hello, I'm Anna Mackay and today we're looking at operations with plain vectors. So a refresher here, for vector A, when you see it in textbooks or on screens, it's often written in bold, but when we write them by hand, we need to use the arrow across the top. And the components of that are, we tend to write them horizontally with square brackets, but you can also see them written vertically with round brackets. And that the first part, just like coordinates that you're used to on the Cartesian plane, the first position represents the x component or the horizontal part of the vector, and the second part is the vertical part. And we have subscript 1 and 2 for those. Same if you have vector B, square brackets, the two components there. Now let's look at one graphically. So if you have vector A as such and vector B there, notice that vector B starts where A ends, so at the tail there. And then what would this be? This blue vector here. That would be A plus B. So it's the combined vector of A and B. And what would the components of that be? So what is A? A is 3, 2. So let's just check that here. So from the start of A, you're going across to the right 3, so that's a positive 3, and up 2. So that's why we write it in this form here, the 3, 2 with the square brackets. What about B? Where does B start here? We would have 1, and then up how many? Up 4. So B would be written vector B, 1, 4. Excuse the missing square bracket. What about A plus B in total? Let's have a think. It starts here and ends at the top there. How many has that travelled horizontally? 1, 2, 3, 4. And up vertically, how many? 1, 2, 3, 4, 5, 6. So that's the A plus B. Now also having a look at, essentially you're adding the components. So the two horizontal components, the 3 plus 1, that's how you get the 4. And the 2 plus 4, that's how you get the 6. So looking at this, making a rule if you like, when you are adding two vectors, you take the horizontal component in the x position and add them. So notice if these are written horizontally with square brackets, you have to look at the A1, so what's in the first position here and the first position on the second one, and you add those, and then comma, and then you are adding the vertical components, which are in the second position. Just, don't get sucked into perhaps adding those two parts of the first vector and putting that in the first position, and then adding those two components and putting them in the second position. That doesn't even make sense. If you were to graph these out, then you can see which sections that you're adding. What about vector A there, and this one was vector B? So just reminding ourselves what we had here. Same as the previous example. But what about if we had A subtract B? What would that resulting vector look like? So B and subtract B will start at the tip of A, where A ends, but it will go in the opposite direction. Same magnitude, same length, and this would be the negative of B. So if we're A and subtracting B, then our resulting vector is this blue one here. And thinking about how far it's travelled horizontally, 2, and down 2 this time. And how do we represent down? With a subtract. So here's our resulting vector, 2, subtract 2 with square brackets. Notice we've written them with arrows. Okay, so summing that up, what we've learnt here is if you have vector A subtract vector B, what you end up with, perhaps could have gone back over this a little bit more on the previous slide, you have the horizontal components of the first one subtract off the other one. If it's a double negative, the same rules apply, that'll become a positive. So you're looking at always the horizontal components and the vertical components together. What about the negative of A? So what does that look like? So instead of going across 3 and up 2, well, both components are negative. So instead of right 3, it's left 3 and down 2 as opposed to up 2. So both components have essentially been multiplied by -1. Adding that to our list of facts, that our negative vector A is the negative of each component. And our last bit of the facts, what about 2A? 2 lots of vector A. that would look like this. So thinking about how far that's gone across and how far that's travelled up. So 6, 4. So notice what's happened to this 3 and the 2. Each component's been multiplied by 2. So of that scalar of 2. So what we're saying here is if you have a scalar out the front of a vector, you multiply each component by that scalar. Okay, some examples. If we're asked to find 3q, so here is q and we want 3 lots of that. Now this is written vertically with round brackets in this case, but we tend to write it for South Australia, getting prepared for Year 12 Specialist Maths, write it horizontally with square brackets. So you would write that scalar 3 out the front and with your vector here, and you're going to multiply through. So 6, -9. You don't bring the 6 and the 9 together, you leave them as 2 individual components. What about half of p subtract 2q? Now, when in doubt, you could always graph these out. You could use some grid paper and sketch them out and see what you would get to try and create that visual picture for yourself at the same time. So the way you write that out is with the vector, with the scalars out the front, subtract 2 lots of q. Notice how q, the 2 is now sitting at the beginning of the pair and the -3 is in the second position. And what you do here is this half has to be multiplied through by each component. So a half multiplied by 4, that's what we have there. A half multiplied by, remember, these are the 2 horizontal components. So you have to now take into account here, -2 times by 2, that sits here in the first position, comma, and now you're doing the vertical components. So you take what's in the second position each time. So a half multiplied by 1, that's what we've got written here. And then -2 multiplied by -3, that's what we have written there. And then tidy them up to get -2, 13/2. We tend to use improper fractions as opposed to mixed numbers. So even nearly I stuffed that one up. Just be really careful with the 2 positions. If you wanted, you could do the multiplying through to start with, and so that you're just left with 2 vectors without scalars at the same time. That would be fine. Now this one here, we're writing this one by hand. So we've got in unit vector form now, and here we've got vector p and q with the I and the j components there, and we have to find that. Do you remember what that modulus stood for? It's the magnitude of that vector, so how long it is. So first of all, what you have to do is I would write out p take 2q and using arrows to represent these as vectors, because otherwise they're just variables. Back when you've done algebra in previous years, you have to define them to be different and therefore that they're a vector, and the way you do that is with the arrow. Then you write out the components here. So p is 3i take 5j, and then we're subtracting off 2 lots of q. Use brackets please, where q is this. And now I'm going to put in my arrows. Working this out, so expanding the brackets. Noticing that it's a positive 2i there and a positive 4j at the end. And then we're collecting like terms essentially. And we're left with 5i subtract 1 lot of j. You can put the 1 out the front of the j if you like, but we tend not to. Now working out the magnitude of this vector, and from a previous slide we know that that is essentially using part of the distance formula. So the 5 I'm getting here because it's the component of I and the component of j is -1, so it's an add here, -1 all squared, and the square root of all that, we have 25 plus 1, and therefore the magnitude is the square root of 26. Okay, join me for the next video for the vector between 2 points. Thank you.